This video is not so much about explanations, but about applications. In the last several videos, we've explained oxidation, oxidizing reagents, how they fit together, why they look the way they do, how they behave, the mechanism behind them. And in this video, I'm going to assume that you've understood all that you've worked through those videos. And so we're just going to apply that knowledge to specific molecules in exercise 13.22. Now a key thing here, because these are really synthesis type problems, a key thing is just to know how reagents affect certain functional groups. Now, it'll be tempting, if you skip to this video without watching the other ones, it'll be tempting to say, oh, this seems really easy, why would I spend the extra effort to learn how these reactions are working? And the answer to that is that if you don't, it'll be hard to remember these specific reagents as you try to learn over 100 of them in this class. And you won't really have an understanding. So as you go from this class into biochemistry, if you have an understanding of the concepts, biochemistry will really just be review and application of the same principles. But you won't see the same letters. You'll never see PCC or sodium dichromate in biochemistry, but you will see oxidizing reagents. The mechanism will be the same, even though the letters won't. So investing in time in getting an understanding will really benefit you, I think. But okay, let's assume that you have that understanding, and here we'll apply it to these specific exercises. Well, what we have is PCC. We have PCC, and what you'll notice, the CH2Cl2, that is methylene chloride. We talked about that in a previous video. That's the solvent here, so that you don't have to use water, because it's the absence of water that prevents PCC from oxidizing primary alcohols all the way to carboxylic acids. It's because there's no water that you stop at the aldehyde. So what PCC is going to do is it will oxidize primary alcohols to aldehydes, and it won't do anything to aldehydes. It won't oxidize those further. So we have an alcohol. What type of an alcohol do we have? And here, let me just, so I can mark it up, I'll put that over here. The type of alcohol we have, let's look at the carbon that has the OH on it. That's bonded to just one other carbon. So that is a primary alcohol. And PCC turns a primary alcohol into an aldehyde. So we can erase this H, draw a pi bond in, and if you want, you can draw the hydrogen in. It's good practice to do that for aldehydes. And that's it. That's the product. PCC will oxidize primary alcohols to aldehydes, and it won't oxidize aldehydes further. So the primary alcohol will turn into an aldehyde, but the aldehyde won't change at all. And so that would be the product you'd expect for that. Okay, next one. Here we have sodium dichromate in sulfuric acid and water. And if you watched the video for the mechanism, you know what that sulfuric acid and water is doing. You have to include the sulfuric acid and water in the recipe when you use this for a synthesis. So in this exercise, they happen to give it to you, but in the synthesis exercises that we'll do later, you'll need to list all of these things if you want to use a strong oxidizing agent. Okay, well, what type of alcohol do we have? You look at the carbon that has the OH on it. It's only bonded to one other carbon, so it is primary. This is a primary alcohol. What does sodium dichromate do to that? Sodium dichromate turns primary alcohols into carboxylic acids. And it would oxidize aldehydes if they were on the molecule. We don't have any aldehydes here, so what's going to happen is that primary alcohol is going to turn into a carboxylic acid. That same carbon, you'll just add a carbonyl onto it, a double bond to an oxygen. And that's it. That would be the product for that reaction. Okay. And like I said, if anything I'm saying doesn't make sense, if it seems random or just something to memorize that doesn't mean anything, I strongly encourage you to go back and watch those previous videos. for this chapter. Okay, here we have excess chromium trioxide in sort of water. Acetone here is just serving as a solvent. Acetone is the smallest possible ketone, and so it's more or less inert. It'll just act as a solvent here. So you don't have to worry about that. The focus here is this oxidizing agent, the strong oxidizing agent, the chromium trioxide. Remember, that's one of those strong oxidizing agents. So that will oxidize aldehydes to carboxylic acids. It doesn't stop at the aldehyde. Remember from the mechanism, for the strong oxidizing agents, first you oxidize the alcohol to an aldehyde and then to a carboxylic acid. So the strong oxidizing agents are capable of oxidizing the aldehydes. And so the aldehyde will turn into a carboxylic acid. And the alcohol, if it's primary, will turn into a carboxylic acid. Notice the carbon that has the OH on it is bonded to just one other carbon, so it is primary. And so that primary alcohol will be converted to a carboxylic acid. So the carbon that has the OH on it, you draw a carbonyl there, carbon double bonded to oxygen. And so that would be the product for that oxidation. Used a strong oxidizing agent, so it turned primary alcohol into a carboxylic acid, and it turned an aldehyde into a carboxylic acid. Okay, next one. We have PCC in methylene chloride. Remember, this is a solvent. There's no water here, so this is going to stop at the aldehyde. So the product you'd expect is, you notice that you have this carbon that has the OH on it is just bonded to one other carbon, so it's primary. And PCC turns primary alcohol into an aldehyde. So we'll erase this H here. We'll draw a double bond, so you have that carbonyl, and now this carbon is the carbon of the aldehyde, so you can draw the hydrogen in. And that's it. That's the product you would get for that oxidation. You turn a primary alcohol into an aldehyde. Okay, how about this one? So here we have an alcohol. We're using PCC, and again in methylene chloride, CH2Cl2, it's methylene chloride. That's just the solvent here, so we don't have to worry about how that would be influencing this reaction. The crucial thing about this reaction is that no water is present, and that's what they're emphasizing by including that solvent there. Okay, so what type of an alcohol do we have? We have this carbon that has the OH on it is bonded to two other carbons. This is a secondary alcohol. PCC will turn a secondary alcohol into a ketone. So you'll erase that H and just draw a pi bond in. And that's it. That's the product you'd expect. Okay. Next. So here, again, we have a strong oxidizing agent, sodium dichromate, and sulfuric acid in water, and all three of those elements need to be present in order for this strong oxidation to work. And the type of alcohol we have would be this carbon here that with the OH on it that's bonded to two other carbons, that is a secondary alcohol. When you use a strong oxidizing agent like sodium dichromate on a secondary alcohol, you end up getting a ketone. So what you'd do is you would erase that hydrogen there, and you'd draw in a pi bond. So notice that if you have a secondary alcohol, a PCC and sodium dichromate, the weak and the strong oxidizing agents, end up doing the same thing. They give you a ketone in the end. All right, and that is it for applying the concepts that we learned about these oxidizing reagents to see how they affect syntheses. So that's just one step altogether. In the next videos, we're going to be talking about multi-step synthesis, and these oxidizing reactions will just be one part of a larger problem.